Okay, let's get started. So, I have to make sure the computer doesn't die on me. And if that is the case, I'm happy forever after. Excellent. Good. Now, another happiness. Number 13, maybe. That's correct. We've done pretty much the most important things to get you started, from linear control to nonlinear modeling to nonlinear control. And that kind of, with this kind of knowledge, you would be able to control robots to some level of complexity quite nicely. The devil is in the details, as you will notice with many things. When you work with a robot, try to figure out the hardware, software, all the details work out. Massive numbers of equations of motion written in C code suddenly supposed to compute something which is accurate. But that's a big practical topic, and I hope you will experience that within our robot to some extent, that you actually see how this looks like. And you will see the world is absolutely not perfect. But what I want to go in today is essentially an annoying problem, which is planning, trajectory planning in general in robotics, and how to go for that. And this could be a complete course by itself. Planning is a really complicated topic. It's a topic which is being addressed in artificial intelligence in many ways. It's a topic which is addressed in robotics repeatedly in many, many different ways. And I just give you a little glance at planning and how to get going, and what is the kind of cheap version of doing it, which is usually using kind of polynomials or splines or something like that, which is nevertheless a very successful thing if you just want to get going. And again, if you work on the details, you will run into problems later on. But you will see a little bit what people are up to and get a feel for that. Planning, in some sense, after you have a control system going, many people treat planning as largely independent from the robot itself, which is not entirely true that you can do that. So for kinematics, for instance, you cannot violate the workspace of the robot. So either you stay inside or you can reach something or do something. But there's also people who would like to start to think about planning which includes the controller as well. So some control algorithms, for instance, look into automatically setting PD gains while they're planning a particular movement. Or some people think about, could we actually plan contacts in a particular way? So it turns out that basically just moving your arm around like this is kind of cool, but it's not the most interesting thing in the world. Most of the interesting things require contact with the world. And controlling these contact forces together with your motion planning is relatively complex, despite all of you do that every day incredibly simply. And there's kind of discrepancies between what we know in robotics or AI, how to plan. It's all heavy-duty search and computation, and all of you do it literally on the fly in a very simple way. Not discounting your brain's ability to compute. Just somehow I don't believe it can be so complicated as we make that in science frequently. Good. There's the picture. People plan all the time. They talk about planning. They talk about optimizing for planning. They talk about simple plans. They talk about reactive plans. You get a little bit of all of it. So let's get going. Fine. That is something we talked about many times, and I cannot re-emphasize it's a great way to get started. For every task we care about, we need to create this control policy. Okay? U equals some policy of the current state, potentially time, and potentially some parameters alpha. Again, important, these are vectors. The alpha would be a vector as well, most likely time is a scalar. If you can figure out this function for every task, you're done with your planning. Actually, you're done with your control. This function includes planning and control in one big picture. It's a nice way to get started. It's just, now you can always start, this is the general setup. This is what I want to do. How do I instantiate it? How do I structure this function? Can I substructure it? Can I make it simpler? Or do I have to deal with a full complexity? Full complexity. How about this? There is a very old topic in the world since at least the 40s, 50s, which is called dynamic programming or optimal control in general. And the idea is, how can you generate these control policies in an optimal way? And the idea is relatively simple. And it's the simplest way, it is basically explained in a computer science world. What do computer science people do? Well, they discretize the world. Okay? So let's make this a 2D world, which is x1 and x2. Assume you start here, and I really make this more now an AI-like problem. I want to get here. That's my goal. Okay? Let me just close the door because there's a meeting. So just close the door when you come in because the meeting next door gets a little bit louder. So, and let's assume we create some obstacles on the way. So this, you cannot traverse through these things. And you get a cost function which says you get a penalty. So the cost function J would be you get a penalty for every time step you're doing. So over all time step T, and you get in the end, big reward, let's say 100 if you reach the goal. At the goal. Okay? So whenever you walk around, you pay until you reach the goal, then you get money. So obviously what you would like to do is you want to take the shortest path to get to the goal. So typical AI style thing. And then you can basically now try to compute how do I get there, okay? What is the right path? You could just try it out, and we'll talk a little bit more about this in an optimal control lecture. Compute the cost, try something else out, compute the cost. But it's a very reasonable way. So this is essentially what is called Monte Carlo experimentation. You just try something out, get the cost, try something out, get the cost. If this one was cheaper, well, you keep this as your best possible, and keep on going. So you can enumerate everything if you want to. You can, in this little world, you can exhaustively enumerate everything. Later on, it becomes more complicated. Dynamic programming, which is basically a subset of what is called reinforcement learning, just formalizes that. It has basically a rule which says if you are on the optimal path and you do one step forward, then you should do the optimal step forward, and from then onwards, you should basically choose the optimal path again. So let's assume I'm here. Now let me. And let's see, what is the optimal? There's many optimal paths actually here to get there. It's not particularly interesting, my example. So that would be definitely one optimal path. But the idea is when I'm here, I can look around. Where can I go? I can go here, there, and there. Okay? And I could potentially compute the cost for each of the states where I'm here. So let's call for this cost there's some J, and for this cost for this state is a particular J, and for this one is a J. I can just number them 1, 2, 3. Stupid numbering. And I basically can say, okay, if I'm here, I have to pay -1 to get to each of those guys. And then basically, okay, -1, but how expensive is it from there to get to the goal? and hopefully one of them is the cheapest. And then I would basically say, okay, I take basically my current payment, and I take the cheapest guy, and from there onwards, it's going to be the cheapest to go. In reality, what people do is they compute this backwards. So you start at the goal, basically, from here to get to the goal, from here to get to the goal, from here to get to the goal. After I'm done with this, I do all those states, and I sweep backwards, and this way I can compute what's optimal. So people have seen this most likely as Dijkstra's algorithm to some extent before. It's a part of dynamic programming. There's generalized versions to that. The world of dynamic programming, reinforcement learning, has its own versions of doing that. But that's the idea. You basically try to chain backward what is optimal and compute what is optimal. It's much, much harder to do this, unfortunately, in continuous systems. So in discrete systems, we have something which is called Bellman's optimality equation, which basically says when I'm this kind of J value at a particular state X has to be some immediate reward I get in X plus the optimal cost at the next. So this is kind of what Bellman's equation says out. There's a consistency if you're on the optimal path. If this consistency is violated, you know that you can improve and can learn something. In continuous systems, this becomes the Hamilton-Jacobi-Bellman equation, which is the basis of deriving essentially these value functions. I should have called this J or V. So forget myself. We just replace all my J's with a V, and that's the value function. So cost functions are often called J, and then value functions are called V. The value function is always this thing which tells you what is the long-term reward to get there. The cost function, the immediate cost function, is actually what you pay at every moment of time. So that is usually denoted with R. So R, if I go from here to there, would be -1. It's very simple. If I go from here to the goal, I get +100. So that's nice. Cool. With these frameworks of optimal control, again, we have one lecture on that in particular, you can compute really complex, totally non-intuitive plans. It's very powerful. So one example which people use a lot in the kind of AI-ish/control literature is the mountain car. So a very simple example. Here's home. Okay, you want to go home. You always want to go home. It's good to go home. And here's the little crummy car which you bought for $500, which only runs on one cylinder anymore instead of some 6. And it turns out if you try to get up the hill, you get stuck. You don't have enough power. So what are you going to do? Well, intuitively, for you all of this clear, you basically go this way, then you go this way. You just until you make it up. You just basically gain momentum. Now, dynamic programming, reinforcement learning, they can find these kind of policies, which are quite non-intuitive. Whenever you have a policy which basically says, on the way to the goal, go away from the goal, that's non-intuitive. And that's not what normally we want to do. Okay. Now, this is in the discrete world. In the continuous world, we cannot enumerate the states. We cannot basically discretize the world anymore, and you get into these partial differential equations, which are just much, much harder to work with. Essentially, in a continuous world, we cannot do full dynamic programming or reinforcement learning. We can only try to find a first shot to get to the goal, and then locally optimize around it. And that's what many people are doing these days. So I don't go into all of this. There's important little things. Some of these algorithms require what is called a model of the system. That means you can predict where you go if you take an action. That means you have equations of motion somewhere written down in some form. In our world, actually, the model was super simple, okay? Which I just showed you before, just like a simple grid world. It simply says, if I'm here and I take an action to the right, I end up here. It's a very, very trivial model. It's called a simple state transition model. Reinforcement learning basically has worked hard. This is basically a topic in machine learning for the last 20, 30 years, where people try to get rid of models. How can you learn without models? You can learn without models. You just learn much more slowly. But you can learn much better if the model you have is wrong or very, very hard to get. And well, you basically, everything goes around this kind of computing this value function. And if you have this value function, you automatically get the policy. So how does that work? Well, it's very simple. So again, if I'm here, and I know now, let's take the proper V notation. I know V here, V2 there, V3 there. Then from knowing the value function, the best action to take is where V is minimal in my next step. So knowing the value function implies knowing the policy automatically. But people are kind of annoyed sometimes since you spend a lot of time creating the stupid value function, which is actually non-trivial to compute, while what you really want is the policy. And so many people say this is actually a stupid approach, but that's still out. Okay, so this is kind of the bigger picture, how to do things more or less optimally, except optimality is not easy to compute, and really, really, really super important. Optimality requires someone gives you an optimization criterion. And making up these optimization criteria is really hard. Okay, let me give you one more example before I go into much more mundane things. So once upon a time, long time ago, I had a little robot which actually had a ping pong paddle. There was basically a robot arm attached to it. It looked like kind of a linkage like this, and it was somehow a motor attached here which could turn this up and down. Essentially made the paddle go straight up and down with this kind of parallelogram. There was a ball which was meant to basically bounce up and down. So I was really excited and trying to do this as an optimal control problem. So how do I do this? And I said, okay, let's create a cost function which basically rewards me if the ball has a low variance at its height, at its bouncing height. That's reasonable. The basic one is that it basically bounces up over time, up and down, and it always goes to the same spot. Okay, so I basically program that, had my robot learn that. Brilliant solution. Actually, the ball was just lying flat on the paddle. It was just being moved up and down. And that was the low variance solution where the ball was always at the same height whenever the paddle was at the highest point. And it took way more terms in the cost function to make this thing actually bounce on the paddle, to exclude all the kind of special cases which you run into. So cost function design is actually very painful and totally non-intuitive, since you play with a very abstract formulation which you don't really know how it's going to be translated by the algorithm into behavior. It's also, just as an aside, there is a lot of people in robotics and control who dislike optimal control. And just, I will give you this example in a few weeks again, but here's this one example which is still fun. Okay, here we go. I'm very nice. This is a abstract sketch of the Grand Canyon. Okay, it's like a big stitch. So there you go. Okay, and you are standing, say, up here, and you want to go on the other side of the Grand Canyon. So my 3D drawing, perspective drawing, all this quite average. Okay, now it's pretty cool. So there is now, let's put you here. Little guy having a good time. Want to be over there, get some beer, whatever drives you in life. And now here, over there, is a beautiful bridge. Okay, 3-way highway, 2 lanes to get over, whatever, big highway. And here, it's a balancing beam across the Grand Canyon. Now, if you just code, I want to go as quickly as possible over there, and the balancing beam is wide enough, well, the optimal path is clearly to go there. But one mistake and you're dead. So from a very practical point of view, the optimal path is definitely to go to cross the big bridge if you want to survive a little bit longer than the next few days. And that's kind of this interplay between optimal control and kind of robustness. Optimality often finds the most obscure solutions to accomplish a particular goal, that they're absolutely non-robust. If you did not take into account all possible pitfalls of the world, you may just be thrown off. So that's just the little example, which control theoreticians would use against optimal control. You can, of course, try to code robustness in some form, but it's actually not so easy. Now, let's become much simpler. To avoid this entire mess with computing optimal trajectories, we can just make them up ourselves in a particular way. And so we don't create the entire policy, we just say, let's create a spaghetti, let's call it a trajectory, and basically then run this into our favorite controller, negative feedback controller, plus a feed-forward term, and run through the movement system. This is how I know how to do that. And so we basically change our policy, for instance, to be just a simple PD controller, which has as a component in there the desired trajectory, position, desired trajectory, velocity. And now you actually notice how this kind of time-varying component comes into the policy. So since the desired trajectory actually now does depend on time frames. And this also depends on some parameters. You can make your gains, for instance, parameters. And you could, at some point, tune them to get better. But this is the most standard way what people do in order to circumvent the entire problem of trying to create the optimal trajectory, the optimal policy. They just say, okay, let's just make something up, a desired trajectory in a particular way and work with that. Which doesn't mean, as you will see in a second, I will reconnect to optimal control. You can make up desired trajectories in an optimal way as well. But if you just want to do something, often why bother? Many things can be done by humans intuitively quite nicely, which may not be the most satisfying way from a research point of view, but nevertheless. Okay, so we need to basically talk about where these trajectories come from. We can worry a little bit about how you use them and modify them online if something happens which you did not basically plan for. And also how to generalize them. But let's do a very simple example. So, cool. Important remark, should not forget, that's why it's written there. There is a big difference between paths and trajectories, okay? That's the big difference often between AI and style and control style planning. Path just means how to get, this was in my grid world, how to get from A to B, not telling you at all at which speed you go there. Now, in a grid world, this is great, or if you play chess, since there is essentially no real dynamics in there. In a practical robot, you want to make smooth and nice movement. If you do jagged movement, it's really stupid. So trajectories are more important than control. We can plan now either in external space or in joint space. It does not make a huge difference, except that the formulation has to be different a little bit depending on what you want to code. And the annoying thing is now, if you want to go simply from A to B, you have essentially an infinity of how to get there. I can go on any path I want. I can go at any speed profile I want. So you can choose. And then the question is, can you basically make this a little bit simpler? You also want to basically think about how do you want to parameterize somehow your plan, if possible. And then you can think about, well, do you need a parameter per time step? That basically goes back to the grid idea that for every time step I would have a grid cell. That is a very fine discretization, or can you do something which is a little bit bigger, like only have a start and a final point? It goes a little bit to this idea of what people call movement primitives or basis behaviors or whatever, what did people call it? Options, macros, there's all kinds of names. It means, can you actually find some kind of chunks, more basically pieces, planning pieces, which are valid over an extended amount of time and which you can reuse as much as possible? And the judge on that is totally out. There are some people who believe you should replan everything whenever you need something. There are some people which says, oh, let's try to just have a very simple plan and make it very reactive. There's people who store away every trajectory they've ever experienced and try to search through them and connect them together. All possibilities are there. Nobody has a perfect answer. It really also depends on the application domain. So for instance, in computer games, so like this kind of Kung Fu, whatever silly nonsense these guys are doing, that works quite nicely by having trajectory libraries somewhere. They quickly index and just concatenate them together. Since these guys do not move in arbitrary ways. They just have a certain maybe movement repertoire. And for you as an end user, if they have about 100 different moves in there, you hardly notice then that this is a discrete library. It feels like a continuous library to you. So different areas need different things. If you have a robot, which the nice example actually, Roomba robot. You guys know the little vacuum for cleaning robot? This is a purely reactive robot. Not quite, has a little planning component these days. But initially, it was just wall following, obstacle avoidance. It was just reacting. It was not planning particularly ahead. It was not using trajectories or something like that. It just looked around, where am I, tried to localize itself and figure out where to go. That's a very reactive way of doing things. OK, let's plan a little bit. And a very nice way to get started is to plan a movement between a start and an end point. Since a lot of what we do is actually point-to-point reaching movements. And so we can basically draw this. Here is time. Let's make this here my goal. And that is just one dimension. So I make this super simple. You start here, and we arbitrarily say we start at 0, that's what we call it. And at a certain time, let's call it tau, you might want to be there. Now, how do you get there? But if the moment you draw it like this, you can actually make stuff up. Okay, well, how about that? Very reasonable. It's a straight line. How do we go there? Interesting becomes in all these considerations then essentially, given that we often want to use velocity and acceleration signals for a decent controller, let's look at velocity and acceleration signals as well. So we also look at x dot, time, and we look at x double dot. Now x dot here would basically look like constant velocity until we did this. And from an acceleration point of view, what you're going to do, you have an infinite spike to get started, which I cannot draw, so this goes out. Then it has 0 acceleration, and then it has an infinite spike to break down. So if you get these infinite spikes into your inverse dynamics controller, you will not get a very happy robot. It looks like, and you break some motors, or it's not a happy robot for sure. Okay, so that's essentially where I'm now going. I'm going to some kind of making stuff up. And it's easy to start with polynomials. Actually, what people in industry have been doing a lot of time is actually that they create velocity profiles, which they like to follow. And so one of them is this kind of trapezoidal velocity profile, which creates a movement. What is it? We have this. We have to integrate this. Create some kind of a nice duct like this that goes constant velocity and creates a nice break like this. So these are little pieces of parabola, since I know that the derivative of a parabola is a line. So that means I start thinking polynomials. And that's why I'm actually going to go into polynomials. Polynomials are a useful representation to think about. So remember, polynomial is simply I say x of t equals a plus bt plus ct squared plus t to the 3, and I can keep on going as much as I wish. And we know from basic math that if I make this long enough, I have an arbitrarily complex representation which can almost represent anything, as long as it's smooth. Okay? And then basically, you're going this, and then you can start discussing, so what polynomials are actually nice polynomials? And we started with one which basically said, x equals a plus bt, that was my straight line. And when you have a representation like that, just reminding you, if I do x of t equals a plus bt, then I automatically get that x dot equals a. No, sorry, b. A drops out. A and b are constants, okay? All these things. And x double dot equals 0. Oh. And if I know that I want to start with x at t equals 0 equals 0, then basically, let's do that. X of t equals 0 equals 0, this automatically leads to a to be 0. Remember, these are boundary condition problems which you learned at some point in school. And V I would get basically from the slope, which I want. Basically, what's my start velocity, which I want, and then I get it. Okay. So let's draw a little bit. So we've already went through the simple first order polynomial. We can do a second order polynomial. Get rid of this. And what does the second order polynomial look like? So second order is a parabola. So fine, parabola I could, for instance, make like this. Okay, cool. That would give me a straight line velocity, something like this. And I get essentially, what does my acceleration look like? So we have here plus ct squared, and x dot equals b plus 2c, and if I should be 1 t left, and x double dot should be constant then 2c. Okay, so I get a constant acceleration out of this. If I may do something wrong, let me know. Constant acceleration, but if you still have a jump here, these continuities are annoying. So that's why people don't like that so much, because you basically, if you have a discontinuity in the acceleration, you basically start from 0, put it up to a value. Again, you get that kind of grinding noise in your robot, which is quite unhappy. So second order polynomial, maybe not the perfect one. Let's do more. Let's do a third order polynomial. Plus d t to the 3. Oh god, all this differentiation. Plus 3dt squared. So my velocity now becomes parabola. And my acceleration, if I do this again, is 2c plus 6 dt. So that's a line. And what you get out of that is actually something which most of the time would look like this. This, like this. Turns around. Should be a little bit nicer. We could do that. You get a velocity which looks like this. And you get an acceleration which goes actually initially up and then goes down with a line like this. Okay? So I'm using the whiteboard, but it's just a line and just jumps back. It still has these jumps at the beginning. The velocity now has become quite nicely. It's pretty. This is still a little bit annoying. But it's actually these third order cubic polynomials are one of the representations people like to use a lot. Since what is nice about it, and I'll show you in a second on a slide, you can basically get the boundary conditions for start and end position and start and end velocity coded very nicely. We can go more. We cannot play this game until we die. But what people also like a lot are fifth order polynomials. So we now go and have to do d e to the 4 plus f t to the 5. And it turns out those guys have very, it's the first polynomial which has really nice properties. It's really smoothly going up here. So it starts with a horizontal tangent and a horizontal tangent here if you take the derivative. The velocity profile would look like this. Notice that again, I'm smoothly going out and smoothly going back in. And I did a bad job with my t x double dot. This would now look like this. And that's nice. Now you have continuous smooth signals in position, velocity, and acceleration. Okay, so you can play with this. The problem is, so why wouldn't you just go and take increasingly more coefficients until you die? You could. The interesting thing is, when you do polynomials, and we have to somehow constrain these coefficients, A, B, C, D, E, F, G, whatever at some point, you can constrain the polynomials at particular points, usually at the beginning and at the end. You can also take intermediate points if you want. But you have no idea what's happening between the constraint points. So, for instance, this fifth order polynomial is so beautiful and so smooth, but if you would compare it to a third order polynomial, you will actually figure out that third order polynomial would create a velocity profile. I'm not good at drawing these things. It would be a little bit fatter like this, but it would be lower. I'm just exaggerating this a little bit. It wouldn't be like this. So the third order polynomial actually creates lower peak velocities. It means it will also create lower peak accelerations. So it actually puts less demands on your motors and your system. And so there are certain trade-offs where you start actually thinking about what is good or not. What can actually happen with the fifth order polynomial if you do a very short time movement, it's just massive accelerations and decelerations, which you can hardly realize. So all looks great if you use it on a big time scale, but the moment you basically go into tricky situations where you mention, oh, I need to do a small corrective movement of 100 milliseconds to get there, and then you do these things, and whee, you do these very high acceleration spikes, which may kill you and create a lot of vibrations in your robot, and suddenly the stuff is not good anymore. Okay. Let's see. So here's a typical example, kind of boring. How to constrain a polynomial, and let's just take the cubic polynomial as kind of the vanilla polynomial representation, which people like because it's easy to work with and has it's conservative in what it's doing, except that its accelerations jump. So fine, here's the third order polynomial in position, in velocity, in acceleration. Now you assume someone gives you a start and an end point. So these are your constraints. Okay? And you need to constrain 4 coefficients, A0 till A3. That means you need 4 boundary conditions, otherwise we can't constrain them. So these are 2 conditions. And then you can add additional conditions. You could say, I want the start and end velocity to be 0, for instance. But you could also say, I want the start velocity, start acceleration to be something in particular. Then you have no control over the end velocity anymore. Or you can do the same with the end velocity. You can also see if you had a fifth order polynomial, you have 6 coefficients. That means I can specify position, velocity, and acceleration at the beginning, position, velocity, and acceleration at the end, which basically gives me that nice smooth movement which I have over there. And then you basically do boundary conditions. So you say, okay, if the start position is at t equals 0, so if I plug t equals 0 in there, all these coefficients drop out. So I get, for instance, that A0 has to be my start position. It's very straightforward. Same I can do with velocity. If I have a start velocity, let's basically plug t equals 0 in there. I have only A1 left. That means A1 is my start velocity. So the t equals 0 boundary conditions are very straightforward to use. We do the same thing for the final position. You need the movement time, tau. Plug this in. You already know A0 and A1. And then you basically have to solve for A2 and A3 based on your final position, and you have another equation for the final velocity where A2 and A3 appear. So you have 2 equations with 2 linear unknowns, and we agree that we can solve that. That's essentially what comes out here. Well, you have to solve that, so sorry. But I haven't done this. But it's kind of okay, I believe. Okay, so next question then to ask is, we now agree on some kind of a polynomial. What do you do if life is not as simple as reaching from A to B, but rather you might want to say, on the way to go there, here's an obstacle at this particular time. So I want to go around it. Okay, so I want to go somehow around like this. Now, this cannot be represented, for instance, by my cubic polynomial anymore, also not by my fifth order polynomial, since this is just too complicated a curve. And you have 2 choices now. You can basically make this longer, add more coefficients, and somehow code that point as the intermediate boundary condition, which is at a particular time. Let's call it tau middle or whatever you want. And then you get additional boundary conditions. You just solve for the coefficients, the extra coefficients you got. Or you do something where you start concatenating simple polynomials. That's what people usually prefer. So instead of basically planning a complicated polynomial, I split this up into two parts. I do a cubic polynomial from here to there, and then a cubic polynomial from here to there, for instance. It essentially doubles the number of coefficients. What is nice about it is that at the kind of joining point, that's where I put it usually where I care about, like close to this obstacle or a little bit away from that. At this joining point, the boundary conditions have to match. That means the velocity at the incoming polynomial has to be the velocity at the outgoing polynomial. The same as the position of the incoming has to be the position of the outgoing. Hopefully, you can also do the same in acceleration. If you do cubic polynomials, that may not be the case, so that may be the case. This is essentially what then most people do, is they basically create these kind of chains of intermediate points. They're often called via points, and then basically do a polynomial to there, polynomial to there, polynomial to there, blah, 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 and get it going. The interesting thing is, remember, polynomials are, just writing this down one more time, a plus b t squared plus c t to the 3 plus b t to the 4, etc. They're linear in these coefficients. So you can actually, if you think about it a little bit, you can formulate the solution for these coefficients as a simple linear algebra matrix problem, where you just solve for those coefficients with some matrix inversion in the end, which is very straightforward. It means you just have to think about it a little bit, then you learn how to stack up all the coefficients. They become all equations which you're simultaneously trying to solve. They're all linear in some coefficients. You can pull them out because they're linear, so they become a vector of open parameters in a matrix, and then you invert the matrix and get those coefficients solved. So basically the idea is get some y equals x times your parameter vector, which would be a, b, c, d, etc. And y and x you can compute from all what you know. And then you can basically get the parameter vector by inverting x, multiplying it with y. And usually that's nicely invertible. It means you can actually compute even long plans with many polynomial pieces really fast in most practical cases. Okay, so far for polynomials, kind of hacky if you think about it. So then people thought a lot about this a little bit more and tried to figure out maybe we can do optimization approaches for the simple representation of polynomials, for instance. So we go back in the world of some kind of a optimization framework where we say, okay, we have some hard constraints like the start and the end and maybe the movement time. And then we have a soft criteria, which can be anything. It has to just depend on what I know. This is, for instance, q, q dot, q double dot, whatever derivatives you can take from your representation that you have. And then the question is, can you actually find the parameters in your representation which is optimizing these criteria? And people have been trying that. There's two ways of doing this. There's what's called the calculus of variation, which is really directly manipulating functions, or dynamic programming, which does that more in an empirical way. But there's some very cool results which came out of that. If you basically have a start and an end point, we just do point-to-point movements right now, and you optimize, or basically your cost which you want to minimize is the squared velocity of the movement. That corresponds to an energy minimization. Remember that energy is equivalent to v squared. So mass times velocity squared. So if the moment, forget about the mass, since it usually doesn't change. So if you just optimize the squared velocity, you usually minimize something which is very close to energy. The optimal solution for that is actually a quadratic polynomial solution. So this thing up to this term, x equals a plus b, is the truly and uniquely optimal, well, whether unique, I'm not sure, but it's the optimal solution to this optimization criteria. Interesting, if you optimize the third derivative squared, that is the change of acceleration, which is also called jerk for some bizarre. And so then this entire criteria is called the minimum jerk criterion, which is sometimes good to optimize for all situations in life. So you want to change acceleration as little as possible, which creates essentially a smoothness constraint. And that, as optimal solution, has the quintic or fifth order polynomial. So that's what I showed you before. So e to the 5 added. Okay. Something is missing. Yeah. The first order term is missing, but let's call this a subtlety, okay? Make it A0 plus A t. Okay. Something looks weird. And so these were kind of cool things, and people figured this out in the 80s, and they were very excited since actually these quintic or these smooth movements look very much like what we humans do when we reach from point to point. So people tried that, and people reach for all kinds of targets, basically record their movements, figure out it looks literally like these minimum jerk trajectories. And then they created also some intermediate obstacles and moved around, and it looked like two concatenated splines of minimum jerk. So it created an entire theory of the minimum jerk trajectory planning in humans. In essence, what it means, we do smooth movements. We don't do things which are jagged. We like smooth stuff. It's just not entirely clear where the smoothness comes from. So you can basically, I can give you a totally discontinuous motor command like step in my view. But I run this through my entire body, and because my body has inertia mass, it will make it look something smooth at the output. But you don't know what the input was. So it's a little complicated to always say what the brain might be planning or what the controller might be planning by just observing something. So there's a lot of things which contaminate what you're doing. And then people got more excited and basically had other criteria. For instance, you can optimize the change of motor command squared. This has no analytical solution anymore, but creates also very smooth and human-like looking trajectories. So people basically over the 80s, 90s, actually early 2000s, came up with all kinds of criteria which they suggested as what the human brain might be optimizing. With a bigger goal, what people would like to accomplish is there this universal optimization criterion which can explain it all? If you optimize this criterion, can you create any behavior you want? And actually, there's a fun researcher at the University of Washington, Emo Todorov, who kind of works with that. He works with kind of optimization approaches and tries to use very simple optimization criteria and says, yeah, oh, from this I can synthesize dancing. Still crazy what he does, but I think it's cool. It's not sure whether he will succeed, but he has cool results, at least that he can do cool things. Okay, now, so I didn't really talk a lot whether it's in joint space or in operational space, but we can take the entire story and say whatever we did in joint space should work in operational space as well, except you need now inverse kinematics to transform it back or some kind of a operational space controller, and you may run into these kind of geometric problems which I mentioned before, but I just repeat them one more time. So when you're planning your end effector, you may just plan trajectories which are not realizable. This robot can never reach here since it always has this long link. This robot here would intersect itself. May not be possible for this robot to do it. This robot would like to go here. It could reach to here, but then it would have to flip around and go basically this way. It could not realize that is either. So these geometric problems you get all the time. And if you try to do this, solve for this trajectory with inverse kinematics, you will basically at some point get a Jacobian which blows up, and you know that something didn't work. If you have problems like that, you cannot do simple planning anymore. You have to think harder how to get around, and that usually goes into the world of AI style planning and search, and is much more complicated. Cool. A little bit more time left, so let me tell you for a moment about another way how people have been looking at planning, and that is a more reactive way. And this comes from this idea of pattern generators, something we've worked in our lab on for a while. The idea is essentially that you have something like some kind of dynamic system, so differential equations, which automatically create movement. And this movement then is given to the arms or to the muscles and creates appropriate goal-directed movement which you want to have. Where does this come from? It comes actually from about 100 years ago. when people were looking at simple animals, like lobsters or insects or whatsoever, and they were wondering how do these insects move. And they came up with very simple models, like if you have, now it's called a neuron here and a neuron there. This neuron excites this neuron excites this neuron, and they both have some state. Let's call this here x1 and this here x2, and you can model these connections with some weights, W1, W2. And these weights can be positive or negative, so it can be inhibitory or excitatory. And you can actually show under the right parameter setting and the right dynamics, so these equations x1 dot are something, and x2 dot have to be something. And they have to be a little bit nonlinear. They don't work if it's linear. You can, for instance, create very nice oscillations over time, so that this here is x1, goes up and down like this. And x2 would be doing something like this on top. That was basically taken as a simple example how to generate patterns, like locomotion patterns, how to move forward. And what's nice about these things, if you go into these representations of differential equations, you can actually change the pattern online by adding something which people call coupling terms, which are this x1 or x2. Like if I put a decoupling term in here, which might be negative, then I basically push the system in a completely different direction. And this way you can think about, well, wouldn't it be nice to have these systems which automatically react maybe to some visual or perceptual input in general, and then kind of go around obstacles automatically and do useful things. This is kind of more this reactive planning, which we all do every day. You know, you do something, suddenly it's in your way, and whoops, you go around. Not clear that you would solve a big optimization problem. It looks like more a reactive policy how to do that. So here's a super simple example why this is kind of potentially nice. We create a very, very simple pattern generator. So this here simply says my desired trajectory, q dot, equals alpha times my target minus the desired. Okay, we've seen that before. We've seen this in Laplace transforms. This is basically, if I put a QF in here, which is different from QD, then and let this develop over time, at some point, QD will go to QF. So what that means is essentially a system which has time here, Q desired here. Here's my, now what I call QF. I let it go here, and it will go up here. And that's essentially it. Which is a nice potential movement plan. It looks a little weird if you look at it from the velocity point of view. So if you look at q dot, it will look like something which goes like this. But there's a very quick movement initially and then slows down slowly. It looks as though I have a reaching like very fast, and then I go very slowly to really reach the goal. But it's a potential way of doing things. And now you can play this game with coupling terms, for instance. So let's add a coupling term to this equation. Q desired equals alpha q target. Is it target? No, final. Sorry, final minus q desired. Now this is my desired movement. Why don't we now reference it also a little bit to reality? This is what this term is doing. Let's add a term plus beta times q desired minus q, which is essentially like an error, okay? The tracking error of how well I'm realizing. And you see, I actually have a plot on this. No, not where's the plot? I'm confused now. I thought I had a plot on that, but I can recreate my plots. So let's basically assume my desire, my real trajectory. So if I do Q in red, and if nothing happens and I have a really good controller, I will track my plan perfectly well and get to the goal. So velocities, that would be Q. But now let's do something crazy. Let's basically say at some point, let's hold my robot tip, so my cube. At this moment, I'm just gonna hold it in this position. Okay? So it cannot go anywhere. So what's gonna happen if I were not using this additional term, but just this term? Well, the plan would just be continuing. So the black plan is completely decoupled from reality at this moment. Okay? Cannot react. If I add this term, it's now actually looking at the error between the desired and Q, which becomes bigger and bigger. Now, if I make this beta less than 0, so it becomes a negative component, then it will suddenly basically create an error, which is currently the desired goes forward, my Q stays behind. So this would here be my error at a particular moment of time. Error grows bigger and bigger and bigger. And if I multiply a positive number with something negative, this would basically inhibit the velocity of my desired. So what will actually happen is that my desired movement will suddenly saturate and wait for me. And only if I let loose, then it would basically continue to go back. And the red movement, basically, the real movement looks like this, stick here, and then would basically catch up. So this is a very simple system how you basically suddenly tell the desired to wait. Don't develop in time unless you notice that you actually make progress. So it's a very simple form of coupling, a very simple form of avoiding you do something wrong. So where does this matter? So very simple example. If you had a spray painting task on a sphere, so here's a little ball, and you basically have some kind of a little nozzle, and you want to spray paint this here nicely. You're supposed to basically move around so it gets really pretty. Okay, you just spray paint this entire circle object. But at some point I hold you. And if you now, the plan would just keep on evolving. Maybe by the time I let loose, your plan is down here. And then what the robot is going to do with a controller, which just goes for the current desired, it would just go straight line there, which would go through the sphere, which is bad. You would have something like this with a coupling term where he would deviate a little bit, then it would wait, and it would go back when it's time. So there's simple examples where you can show that it's a good idea to do it this way. There's obviously examples where these coupling terms make no sense. But it's kind of a nice way to basically combine a desired trajectory generator with an online reactive modification component. Let's see. So find what is good and bad about pattern generators. What is not so good about it is the moment you put together differential equations, it becomes more complicated to analyze. You don't have an analytical solution like in the splines for what you're doing. You often just can only get the solution by doing Euler integration of the equations which you have here. For this one, you could get an analytical solution, but for most of them, you can't. You don't exactly know what the shape looks like. The polynomials give you some handle on the shape. I know it's a lower order polynomial. It's going to be a parabola, so it's nice to know. And usually the modeling with these things becomes more complicated. Just for fun, we've been working on this for a while to try to make this more complicated. So this is essentially what I showed you before. This is the simple first order system going to a goal. See, this is a second order system now. This basically has a goal state. This is like a spring damper system, just written as two differential equations in a slightly different way. So this is the goal where you want to go. Y would be your velocity of the system. No, your position of the system, z is the velocity of the system, and z dot is kind of like an acceleration. But the question is now, can you do something more complicated? Can you actually change these equations so you can do a crazy movement like on the way to the goal, like go backward? We all do this when we play tennis. First we go back, and then we actually go towards the goal. And basically it turns out you can add some kind of nonlinear terms in the equations and then get more complicated things. I'm not going to go into this in detail. You get equations like this, which basically combine machine learning with differential equations, and you can create more pleasant systems. So here's some hopefully working videos, which we used at some point.
how to teach a complete humanoid robot how to do a tennis swing. So this is a friend and collaborator, Alka Eisberg, who's a professor in Switzerland these days. And he basically was wearing an exoskeleton, teaching the robot how to do a tennis swing, and then the robot repeated that. And it actually basically used that ball as a goal. Not very perfect, but it's a little bit of a first step, how to basically go in a really complicated multi-degree of freedom system and kind of transform it with the help of a demonstration into a pattern generator which can go for a goal. Let's see, he did this also with a backhand. I think the backhand is much nicer. Auke is not a tennis player, in case you wonder. So he takes no credit or any kind of discredit for the quality of his backhand. So let me see. I don't want to go. Well, you can do the same thing with periodic motion as well, and this is just using limit cycle dynamics. But this is just fun. It was obviously improvised running in a lab. Again, wearing this exoskeleton and then transforming that pattern into these kind of pattern generators. Okay, the drum was missing. I think which is fun in this video is actually at some point, when you have differential equations, you have also speed constants. You can take them faster or slower. But yet, with speed, you're integrating the equations of motions. Someone can come in, and now you have these coupling terms active. And the entire pattern breaks down, which is really nice. Robot looks at the idiot and keeps on running. This is kind of what you would expect. You don't want that the machine starts fighting you and keeps on going. It's like, hey, and good. Fine. This is research. This is not totally clear whether this is the right way of doing things. This darn video thing crapped out again. I hate this. But it's a nice way of basically combining trajectory planning with reactive control. And in some sense, what we in our research would like to accomplish at some point is combining both. Like there's certain things which you want to do with optimization and planning, but you would like to have plans where you can insert these reactive terms. So I have currently one student who tries to work on how to create with machine learning arbitrarily complex reactive terms, which you might be able to reuse for obstacle avoidance, for force control, or whatever you want. So this is kind of ongoing things. What do we have here? Oh, there's another example. Let's do the last video, and then we're kind of getting towards the end anyway. Okay, so here's teaching a figure 8. The nice thing in these kind of representations is, not that I told you too much about this, what we created, you can actually code literally arbitrarily complicated movements in these pattern generators, and then the robot itself should do it. I think what this one has, this video has a nice component where you can see what the perturbation looks like at some point. So now it's doing it more slowly. Okay, fine, a younger version of me holding it. Look what's going on. I think there's something which is kind of okay. Now looking for it to a television system, just looking at the ball. Into the old days, there was a television and had it connected to it. So this is what the robot normally does. So kind of create a little distorted, but it's okay. Now someone holds it on, basically waits there, and then kind of jumps back on the trajectory, not too far away from where it started. It doesn't jump to the entire trajectory. All right. Small outlook on planning, essentially. It's a huge area. And again, there's like literally, I don't know, I would say hundreds of thousands of people working on the topic, how to do planning in real time for robots, how to do very complex plans. This planning topic is not just a robotics topic. You can take this in lots of different domains, and there are sometimes
optimizing some kind of protein folding, whatever people do become planning problems. There's a huge world out there. Traffic optimization is a planning problem. Lots of things. The techniques are often very similar. The specificities of the application domain is often special. So robotics cares about smooth movement. We care about continuous movement, no jaggedness. We care also about conservative movement frequently. That means essentially, don't try to do something which you have never done, which may actually be destructive to you. My fun example of this is take a 3-year-old child, can stand nicely, it's kind of fun, and throw the child a ball to catch. Those little guys, what they do is basically they have their arms out, they look at you, the ball comes, they hit the ball, and that's it. They don't do a twitch to catch the ball. Like later on, 3 years later, basically, they do, whoa, try to catch the ball really aggressively. But at this age, they're completely conservative. They don't do any movement which they don't understand yet how to do. Doing these kind of things essentially is something we have not fully understood in robotics. Just predicting when we might be failing and do something wrong is really complicated. And people work on that and work on real-time control and optimization to get to these points. All right. What is it, Thursday? I'll see you next week.